Okay, the last question on the document for today. You have 6-volt potential difference, resistance of 10 ohms. What's the current? Well, the definition of resistance is voltage divided by current, and we can always reason that out to make sure we have it correct. More voltage required for a given current means more resistance. More current for a given voltage means less resistance. Voltage has to go in the numerator, current in the denominator when you're defining resistance. Now, you rearrange that very easily. You multiply both sides by the current and then divide by the resistance, and you get this rearrangement, which I'm sure everybody can do easily if you have the law straight. Okay, so the voltage is 6 volts, resistance is 10 ohms. You get 0.6 amps. Now, how do the units work out? Well, the ohm is a volt per amp because the resistance is defined as voltage divided by current. Okay, so the SI unit is volt per amp. We've already seen it. It can be arranged as joules per amp coulomb, joules per amp squared second, joule seconds per coulomb squared, or kilogram meter squared per coulomb squared second, and you should work out all of those. The one that's convenient here is the first, the volt per amp. So we get volts divided by volts per amp, we get amps. We get 0.6 amps for the current. Now the next question is, what's the power, the energy per unit of time? Now that would be in joules per second. Reasoning by units, we can figure this out. And if we go back to the ultimate meaning, we're going to find, well, let's just see what we find. 0.6 amps is 0.6 coulombs per second. That means we have 0.6 coulombs passing at a given point every second. 6 volts is 6 joules per coulomb, meaning for every coulomb that passes, we get 6 joules. Well, we require 6 joules. That's what potential difference means. And we can go back to the roots of that idea, which we've covered, and build our intuition and our depth of insight by thinking about what all that means. But it's expedient here just to say, okay, well, if we multiply a number of joules per coulomb by a number of coulombs per second, it's clear we're going to get the number of joules per second. So we multiply 0.6 coulombs per second by 6 joules per coulomb. We get 3.6 joules per second, or 3.6 watts. And that's the power required to maintain this circuit. So if you're cranking the generator, in addition to the mechanical resistance inherent in the generator, friction in the bearings and gears and so forth, in addition to that, you need 3.6 watts of energy to maintain the current. And that energy, incidentally, is basically dissipated as heat. You warm the wires up a little bit, and they dissipate their energy to their surroundings. Okay, well, we can generalize this. This is your current, this is your voltage. We got the power by multiplying current by voltage, and that's the way it is. If you think again about the meaning of current and the meaning of voltage, this is an obvious relationship. And if you think in terms of units and think about a little more deeply about what they mean, this becomes very obvious. Okay, well, this can be rearranged in a couple of ways. Remember that the current is voltage divided by resistance, so if we substitute voltage over resistance for current here, we get V squared over R. It's another expression for power. It comes from this. This is the intuitive, obvious expression for power, but using the definition, Ohm's law, the definition of the resistance, we can easily express this as V squared over R. Or if we want to replace V with V would equal I times R. So we replace V with I times R, and we get I times IR, which is I squared R. By that substitution, we have these relationships for power. And these are all relationships that are very fundamental and not difficult to reason out if you think clearly about meanings and think clearly in terms of units, which is immensely helpful here.